Hi everyone. This week we're going to delve deeper into direct current electric circuits. Um, and there's a lot of material to cover here, but I do want to say that I think a lot of students find this stuff conceptually a bit easier than the previous several chapters. Um, I don't, or I didn't when I took this myself. So it's really up to the person. But let's move on. We're going to start talking about current, electromotive force, and resistance. And we already know Ohm's law from the previous lesson, which says that the voltage across a circuit element is the current through the circuit element times its resistance if it's an ohmic device following Ohm's law. Okay, so let's move to the next slide and talk about circuits. First of all, there's lots of different symbols that we're going to use in these diagrams. Here are some of those symbols. The most common ones that we'll be using are the resistor, the capacitor, the source of EMF, or what's often thought of as a battery, and the switch. Now, I'd also like to say that when we draw lines in a circuit diagram, a line represents a wire or a connection between two circuit elements, and those lines should be considered ideal wires. In other words, even though it might not be true, they offer no resistance to the flow of current whatsoever. And then we will roll up any resistance that's associated with actual physical wires into a resistor on the diagram. Okay, so moving on, what about EMF? EMF stands for electromotive force, but it is not really a force. When we use the term E, so EMF, we will represent an EMF by a script E like this, and this is a potential difference. It's a potential difference, not a force. The EMF is caused, the potential difference is caused by a force. And what I want you to think of an EMF as is this is supplying electrical energy by doing work on charges against the electric field. So you can imagine the EMF, if this was like gravitational, the electromotive force, or the force in, say, a battery, is pushing the charges uphill. And why would we want to push the charges uphill? Just like water in a fountain, then gravity will do the rest of the work in bringing them all the way back down to zero potential so they can start the process over again. And what we want in a circuit is we want the charges to flow through all of the circuit elements, creating a current. And in order to do that, we need to bring them up to higher potential energy, higher potential energy, so that they will flow to lower potential energy. And then the EMF is the pump or the elevator that brings them back up to the top so they can do it all over again. So that's like a battery or a power supply. It does work against the electric field so that the electric field can do all the work all the rest of the way back down through all the circuit elements. All right, so let's look at resistors now, and suppose that we have some resistors in series. With two resistors in series, the current results in voltage drops across each resistor, and from Ohm's law, we can see that the potential difference across a resistor should be the current through the resistor times the resistance of the resistor. Okay, so V equals IR, and what happens? The voltage drops. It goes down, decreases as current flows through a resistor. Okay, so if I have a battery, and people draw batteries different ways, I usually draw mine like this instead of twice that, which they do in the diagram in part B here. Then we have a resistor over here. That's a little jaggedy line like this. R1, and then we have R2, and then we have a complete circuit. So what's happening here? The EMF, let me label that E. The EMF, the battery, lifts the charges up to higher potential. So if this is the positively charged side of the battery, it will bring more positive charge to that side. It's doing work against the electric field. Now that there's an excess of positive charges, those positive charges will flow through the resistors and back down to the negative side of the battery. Now, in reality, we know that electrons are the things that are actually doing the flowing. So the electrons are building up on the negative terminal of the battery. They flow backwards in the opposite direction of the current. Current is defined as the direction of positive charge flow. So we can easily just understand what's going on by just assuming that the charges that are flowing are the positive ones, and then just recognizing later that, hey, it's really the negative charges that are flowing, but that doesn't matter for the understanding the concepts here. Okay, so now that we have this, the first thing that we have to know is that the current has only one path to take. Here, all the current that goes through resistor 1 has to also go through resistor 2. So the current in resistor 1, if I call that I, the current in resistor 2 is also I. It cannot be different because there's nowhere else for that current to go. Current does not diminish, it just has to go from one place to another because the charge is not able to pile up anywhere in the circuit. If it were, for example, we'd have a charge density increase, say at this point, then that increase in density would push charges away and cause them to continue flowing through the circuit. Okay, so now I can see that the resistors in series, since the current's the same, if I were to replace this with an equivalent resistance, let's suppose that I just wanted to erase these all together and just say I have some resistor here which is R equivalent. It's the equivalent resistance of resistors 1 and 2. Then I know that so I times R equivalent, that's the voltage across the equivalent resistance, is I times R1 plus I times R2. Okay, and so since I know the current is the same through each of these, I can see that in series, the resistors just add. So no matter how many resistors I put, if I put them in a chain, one after the other, so that the current has nowhere to go except through the next resistor, then the total resistance will be equal to the sum of the individual resistors. Okay, let's look at a real battery now. What is a real battery? A real battery is not only a source of EMF, but a real battery has its own internal resistance. So I can draw a real battery as, hey, here's my source of EMF, and then there's some resistor here, and I'll call that little r. And then I will hook this up to a load, which is some other resistor. This is not part of the battery. And I will call that one capital R. And the real battery, an actual battery, is the sum of the EMF and the battery's own internal resistance. Because even though it's working to push the charges uphill, there's also some opposition to that flow of charge. So there is always inherently some actual resistance inside the battery. All right, so now we can think about something which is pretty interesting. Let's suppose that I have 2 points here, and I'll call this point A, and I'll call this point B, right? And then let's put a switch in here. So a switch we draw like this, and initially the switch is open. Okay? When the switch is open, we want to find the potential. Actually, I wrote these backwards. We want to find the potential of point A relative to point B. We'll call that VAB. That's the difference in potential between these 2 points. And what is that when the switch is open? Well, when the switch is open, then no current can flow because the switch is open. It prevents the current from flowing. There's no complete circuit. There's no complete loop here. So VAB, the difference in potential between A and B, is the EMF. If this was a 9-volt battery, we put a voltmeter across between A and B, we would measure 9 volts of potential difference. But now, we'll close the switch. Okay? And when we close the switch, then current will flow. Okay? And we'll call that current I. And the current will flow around, completing the circuit, going all the way around the loop. And when the switch is closed, then the potential of A with respect to B, regardless of whatever load that we have connected here, the potential, I'm not looking at the potential all the way around the loop. I know that that's actually going to be 0 because the electric force is conservative. But what I'm looking at is the potential of point A relative to point B. That's going to be the EMF from the battery minus the decrease in potential across the internal resistor, so minus IR. Right? So this is less than E. Whenever I hook up this battery, say it's 9 volts, and I actually hook it up to another resistor and I allow current to flow, am I still going to have 9 volts of potential? No. It's always going to be less than that. So any real battery will have a lower potential across it when it's hooked up than when it is not hooked up to anything. And that's due to the battery's own internal resistance. Okay, let's move on and look at resistors in parallel. And what do we mean when we hook up resistors in parallel? That means that one side of the resistors are all chained together and the other side of the resistors are also chained together. So I'll draw my battery, my ideal battery in this case. I'm not going to draw any internal resistance because sometimes we just don't care about that. We can have ideal situations to study what's going on. So I'll have a resistor R1, and now I'm going to hook up the same side of R1 to the same side of R2, and I'll hook up the opposite side of R1 to the other side of R2 over here, and then hook those up to the battery. And now what's going to happen? Now, this is what we call parallel. And in this parallel circuit, we have some current through the battery. I'll call it I. And then the current reaches this point, and some of it goes through R1, so that I'll call I1, and some of it continues on through R2. Okay? Then those currents combine back together here. These points where there's an intersection of 3 or more wires are called nodes. So when we have a node, then those combine back, and now we've got this current again, I, which is I1 plus I2. So in a parallel circuit, all of the current doesn't stay together. Some of it flows one way, and some of it flows another way. Okay? But what we can see is, since these are ideal wires, if I label this point A and I label this point B, the potential across the battery, VAB, equals the EMF, but that is the same as the potential across R1. since these are ideal wires, there's no change in potential across them. Really, I could draw it as if all these points, those points, these points, and these points are all really the same point. So I could stretch and squeeze my diagram however I see fit. Could look like this maybe. So that we can really see that those are actually the same point. That means that the potential difference between them is the same. Okay, so this potential across the battery is equal to minus I1 R1, which is equal to, well, let me just say I1 R1 is equal to I2 R2. The magnitude of the potential. Current will flow to lower potential. There's a drop in potential across the resistor. So if I'm going this way, it's a decrease. If I go this way, it's an increase. But the change in potential, the potential of A relative to B, is this EMF. It's also equal to I1 R1 from Ohm's law. It's also equal to I2 R2. Okay, so let's play around with Ohm's law for a second. We'll say that the resistance, remember, V equals I times R. So that means R equals V divided by I. Okay, great. So if I wanted to replace all of this with some equivalent resistance, let's just say we replace that all with one resistor here. And I call this R equivalent. What is the equivalent resistance of the parallel combination? Well, I have R equivalent is E over I battery, right? That's this current right here. That's got to be equal to V divided by, it's the same VAB, right? Same one, over I1, and that's got to be equal to VAB divided by I2. And now we know that the potential here, these are all the same in this case, in the parallel case. They were not the same before in the series case. But what's different is the current through each resistors. These are not the same. So problem is, if I want to determine what this R equivalent is, I don't have a common denominator. And what I should do is I should flip all of these. Let me erase this. Make some room here. And we can say that 1 divided by R equivalent, that's, what did I say? I divided by E is 1 divided by R1 plus 1 divided by R2. And that's because this is I divided by VAB. Okay? And VAB is the same for each of these. So now we do have a common denominator, and we can just add these. So what I'm left with is that the equivalent resistance in parallel is 1 over R1 plus 1 over R2, and then I have to do 1 over that. So I flipped this, so I need to write to the minus 1 power. Okay? So now what we're saying is in parallel, resistors add reciprocally. The equivalent resistance of parallel resistors is the reciprocal of the reciprocal sum. Okay? And that ensures that the resistance, the equivalent resistance, will always be less than the smallest of the individual resistors that went in there. Okay, so you can read through on analyzing component circuits. The way to do this is really to try and start with the smallest unit and work your way outward. Let's try an example. 4 possible combinations of resistors. Let's rank them in order from the highest resistance to the lowest resistance. And all the resistors have the same resistance. Let's just call the resistance of each one. Each one of these guys has a resistance. We'll call it R. All right, so now what about for A? Well, are they in series or parallel? Yes, they're in series. So that means I need to add them up. This is R plus R plus R, which is 3R. Okay, what about B? Series or parallel? Right, parallel. So now I need the reciprocal of the reciprocal sum. So that's 1 over R plus 1 over R plus 1 over R, and then I need 1 over that. Well, this is 3 over R, and then if I flip that, that gives me R over 3. So 1/3 of any one of the individual resistors. It's less than any one of the individual resistors. Now let's look at part C. Well, I first want to break this up into chunks. When I see these two three resistors, and they're arranged like this, then I want to, in order to determine the equivalent resistance, I need to start with a smaller subunit. So I'll look at this guy, and I'll say, okay, well, those are just in series, so I can replace this with the equivalent resistance, which is 2R. And then I have the parallel combination of 1R and 2R, which will give me 1 over R plus 1 over 2R to the minus 1. I need to find a common denominator. So I multiply this by 2, I multiply this by 2, and I get 2 plus 1 is 3 over 2R, and then I have to flip it. So this is 2/3 R. The minus 1 says flip it one more time, because we take the reciprocal of the reciprocal sum. Finally, part D, we have a parallel set of resistors, and then those are in series with a single resistor. So I'm going to start with the small subunit, that's this one, and I know that that's going to be 1 over R plus 1 over R to the minus 1, which is R divided by 2, and then that's in series with this resistor R, so I just merely add them. So this is 1R plus a half R, that is 3/2 R. So we can see that A is the biggest, B is the smallest, D is the second biggest at 3/2 R, and C is the third biggest at 2/3 R. Okay, hopefully that made sense out of resistors in series and parallel. Now this is great for some circuits, but there are other circuits where series and parallel combinations just cannot work. And one of those, often called a Wheatstone bridge, is shown above here. I have resistors R1, R2, R3, R4, and R5. And if it wasn't for R3, this would be a nice, easy problem to solve. But R3, going between those two nodes there, really throws a wrench in the gears. There's no easy way to find a parallel or series combination that allows us to quickly solve for the equivalent resistance of this circuit. Instead, we have to resort to a new way, which is using what are called Kirchhoff's laws. And these are general expressions. They work for any circuit. They're incredibly useful, but it's really important to have the conventions, the things that we use to systematically solve these down pat. Right, it's not simple. There's a lot of freedom in how you choose things, but you must follow the rules in order to get the correct answer. So let's look at those. First, we'll look at Kirchhoff's loop law. Kirchhoff's loop law says that the sum of the changes in potential around any closed loop is 0. Okay, so what am I saying there? Let's draw a very simple circuit. Here we just have an ideal battery and 2 resistors, R1 and R2. And what we're saying is that there's a current through here, I, and that's the same current here, I. These are in series. And we're saying that the sum of the changes in potential is 0. That means because the electric field is a conservative force, that the potential energy in moving from one point around some loop and back to where you started, the change in potential energy has to be 0. That's true for any conservative force. Okay? So what are the changes in potential? We have a change plus E. We're going this way around the loop. It's very important to note the direction that we're going. So this is the direction we're taking. We'll call that the loop direction. And if I go this way around the loop, I have the gain in potential across the battery, because I'm moving this way. And then I have a drop in potential across R1, which is I times R1. And then I have a drop in potential across resistor R2. That's I times R2. And Kirchhoff's law says, since I've come back to where I've started, that change in potential must be 0. Right? This is Kirchhoff's loop law. Now, we could have also drawn our arrow around the loop this way. Okay. Oops, I didn't draw an arrow in there. And if we drew our loop that way, then what would this look like? Well, I cross this resistor, but I'm going against the current. My loop direction is against the current. So I would have plus I times R1. There's a gain in potential energy if I do the opposite thing that the charges are doing, the positive charges are doing. Then I go across that's R2. Cross R2, or R1, and that would be plus I times R1. And then I have to come the opposite direction across the battery. And if I do that, then I would say that that's a drop in potential. And this is, of course, the same equation as the equation up here. Okay. So what we're saying here is you are free to pick the direction that your loop goes. That is completely up to you to decide. If you have many loops in a complicated circuit, you can pick each individual loop to be whichever direction you choose for it to be. But if you're going to do that, then you have to be very careful. I mean, even if you didn't, of course, always, you just have to be very careful about what we call a gain in potential and a drop in potential. So the rules are this. If you go across a resistor in the same direction as the current, then that's considered a drop in potential. And if you go across a resistor in the opposite direction of the current, that's considered a gain in potential. Now, if I go across an ideal battery or a source of EMF in the direction from negative to positive, that's considered a gain in potential. And if my loop direction takes me across the battery from positive to negative, then I have to call that a drop in potential, like I have here. Okay. Okay, so now let's look at an actual circuit with many loops. This is a relatively easy one. You could probably solve this using other methods here as well. That won't be true for all of the circuits, but it's a quicker example to go over this one. So what do we have here? We have 2 batteries and 3 resistors. I've got a battery which is got an EMF of 6 volts, and it's this way. And then I've got a resistor of 2 ohms. And then I have a resistor here, which is 1 ohm. And then I have a battery facing the opposite direction here. And this has an EMF, let's call it E1, E2, is 9 volts. And then a resistor over here, which is 4 ohms. Wait, did I talk about the node law already? Kirchhoff's loop law. Oh, and I haven't mentioned the node law yet. I'm sorry. So let me go back and mention the node law. The node law states that the sum of currents at any node must be 0. Charge does not pile up arbitrarily in a circuit. So that means that if you have charge flowing in, that must be equal to the charge flowing out. And what is a node? A node is a place where any 3 or more wires meet. So these 2 points in my circuit are what I label as nodes. Now, what are the directions of the current? I don't know, and I don't have to care either, right? So the only thing that you have to do, you're free to choose your current directions. But when you do, you must make sure that they follow the constraint that the current flowing into a node is equal to the current flowing out of the node. We can express this as an equation. So let's do that here. We're going to use node A, and we will define our currents. Which way are we defining these currents? We've got, according to the diagram, we have I1, which is going this way. We've got I2, which is coming this way. And then we've got I3, which is going in this way. And that is arbitrary. Are those the actual directions of the currents? I don't know, and I also don't care. Because in the end, if I follow these rules and I'm consistent with the conventions of using them, then I will get a minus sign for any current that I have given the wrong direction to. But the magnitude of the current will be the same. It will be correct. Okay, so now what does my node law say? The node law says that the sum of the currents going into the node has to equal the sum of the currents going out of the node. So if I call the one going in as positive, I would say I3. And what else is going in? I2. So plus I2 is equal to what's going out, or minus I1 that's leaving, so it's got a negative sign. This has to equal 0. The sum of the currents going in, which are positive, the sum of the currents which are going out, which are negative, has to add up to 0. And this is the first expression that I want to write down. The node law always comes first in defining your currents, because when you solve a system of equations, there are no coefficients in front of these things, and it makes it a lot easier to solve. So that's always the first place to start. Once I've written down the node law, I have to write it down for, if I have to write it down for at least one node, and depending on the circumstances, I might have to write it down for several nodes. If I write it down for every node in the circuit, then that would be the easiest way to begin, because the nodes are easier to handle than the loops. So now let's tackle the loops. All right, and here we have several loops drawn. We have loop 1 goes around the inside this way. So we'll label that 1. Loop 2 goes around this inside one this way. And that's totally up to me. It's up to me to decide which way to choose these loops, just like it was up to me to decide which way to choose the currents. And then I have another loop, loop 3, which goes around the whole outside this way. Now, the next thing I have to make sure that I've done is that every circuit element must be crossed by at least one of the loops. I couldn't have something dangling out here, I don't know, that was not traversed by one of the loops. Everything has to be traversed at least one time by my loops. All right, and now I can write down the loop law for each of these loops. So for number 1, I'll start at the battery. I have 6 volts, and I'm going to leave off my units because these get really complicated if I write in all the units. 6 volts, and then I go across this. Am I going with the current or against the current? Well, this is I1. I1 is taking me this way. The way I've defined it, I'm going with the current, so this will be a drop in potential. So I'll have minus 2 I1. Right, 2 because of the 2 ohm resistor. All right, now my loop takes me up this way across this 1 ohm resistor. And the way I've defined I3, this is also a drop in potential. So minus 1 ohm times I3. And then back to where I started. So this one equals 0. Now I can look at loop 2. And loop 2, I start here. I go across the battery, and I'm going from negative to positive. So this will be plus 9. Then I go across this resistor. Which way is I2? I2 is coming along this way, the way I've defined it. So I'm going against the current here. That means that this is not a drop in potential. This is a gain in potential. So I'll have to say plus 4 I2. Okay? And then finally, I go this way, and I'm going with the current I3. So minus 1 I3 equals 0. Okay? If we solve the node equation for I1 and substitute the result into the equation for loop 1, this says I1 is the sum of I2 and I3. So wherever I see an I1, I can just write I2 plus I3. Okay? All right, and we multiply the previous equation by 2 and add it to loop 2, and we get this. 9 plus 12 plus 4 minus 4 I2, and then plus minus 1 minus 6 I3 equals 0. And then we can solve for I3. Wait a second. Hold on. Oh, right. This goes away, and we can solve for I3. So I've got I3 must be 21/7 or 3 amps. All right, so now that I know I3, I can solve for I2 using this equation, and I know that I2 would be I3 minus 9, right? Then divided by 4. I'm off the page. Let's make sure I got that right. So I3 minus 9 divided by 4. And so this would give me minus 6/4, or minus 3/2 amps. So what does it mean that I've got a minus sign on my I2? That means that I was wrong. I2 should actually be going in this direction. It's okay though, because I followed all my rules correctly. I know that that is the correct value for I2. It just happens to be in the opposite direction of the arrow that I've drawn. Finally, I can solve for I1. I1 is I3 plus I2, so that's 3 minus 3/2, which is 1.5. That's plus 1.5, or plus 3/2. So I1 was correct. It's only I2 that had the wrong direction. This is how you solve a Kirchhoff's laws problem. Start with the node law. Always do the nodes first. You can do them for every node on the problem. In this case, you'll find that since we only have 3 currents, you'll get the exact same expression if I chose node B as I would for A. But if we had done an example like this, how many nodes do we have? That's right, 4. There's 4 nodes here, and we have to define 6 currents in order to solve this problem. So we write those node laws down, and that allows us to express this in terms of only 3 currents. That means that out of the, I think there are 7 loops that I could potentially draw in this diagram, I only need to write down equations for 3 of them, because my number of unknowns should match the number of equations that I have. Right? I don't need more than that. So as you can see, these expressions for the loops, because they have coefficients, are much more challenging than the expressions for the nodes to deal with. So we want to start with our nodes, write down all of those equations first, eliminate as many currents as we can by expressing them in terms of other currents. For example, this one we said I1 is just the sum of I2 and I3, and we can forget about I1. Then we write down the loops for however many unknowns we have left in the problem. They might be currents, or they may be, say, an unknown battery potential, or EMF. Could be anything unknown. However many unknowns I have, I need to have as many equations to solve it. And then I solve that system of equations for whichever unknowns I'm looking for. Okay, so that's Kirchhoff's laws. Now let's look at electrical measurements. So a voltmeter measures the potential difference between its 2 terminals. So how do I plug in a voltmeter? Yes, it goes in parallel with whichever object I'm trying to measure the voltage across. And what does that mean about a voltmeter? Ideally, a voltmeter should have an infinite resistance so that no current crosses that voltmeter. Okay? And this should measure the voltage across that unknown resistor in this case. What about ammeters? This is to measure current. Current flows through a circuit element, and we need to then connect our ammeter in series with that circuit element so that all of the current that is flowing through the ammeter then flows through that circuit element. It wouldn't make any sense to put it across the circuit element. So what about an ideal ammeter? An ideal ammeter should have 0 resistance. Right? So there's 0 change in voltage across the ammeter, and it really measures all of the current that's flowing through that device. Great. What about capacitors? When we put a capacitor into a circuit, it introduces time dependence into the circuit. And we can look at a simple example. This is what we call a resistor capacitor circuit, or an RC circuit. The voltage across the capacitor cannot change instantaneously, so there is a time-dependent circuit here. Let's look at this example. All right, so I have a battery. I have a switch. I have a resistor. And then I have a capacitor. Okay, And so what happens when I close the switch? Current begins to flow. So I'll close the switch, and current flows from the battery. Positive charges would flow in this direction, causing positive charge to develop on this plate, and negative charges will be pulled this way by the battery, developing negative charge on this plate. So the charge will begin to flow until the capacitor is fully charged. When the capacitor is fully charged, then the potential across the capacitor is equal and opposite to the potential across the battery. No more charge will flow. Okay? So this is charging a capacitor. All right. We can use Kirchhoff's loop law, and this is just a single loop, to solve this equation, to figure out what's going to happen here, the time dependence of the circuit. So we'll start with, we've got our loop going this direction. We'll go along with the current here. So I've got a gain in potential E. I've got a drop in potential minus I times R. And then what about the capacitor? Remember that the capacitance is given by Q over V. So I can write that V equals Q over C. And the drop in potential across the capacitor then should be Q over C. And by Kirchhoff's laws, the sum of the changes in potential across this circuit should be 0. Right, now we can differentiate. And so we'll divide by dt, basically, and that's because there's only two quantities that are changing here. The current is changing, and the charge is changing. So we can write minus, what's the derivative? Sorry, I'm not dividing by dt, I'm differentiating both sides. Right, so if I take the derivative, what do I get here? I get the derivative of a constant is 0. I get minus r di dt. And then I get minus the constant, 1 over c. And what's changing? The charge. So that'll be times dq dt. And this has to be equal to 0. All right. I can now rearrange this expression. I can write di dt is minus I over RC. And where did that I come from? It came from right here. We recognize that the derivative of charge with respect to time is the current I. So this is a differential equation. It's a differential equation for exponential decay. I know that most of you haven't taken differential equations yet. So let's look at how we can determine that that's true. And an easy way to do that is to separate the differentials and then integrate both sides. It's called separation of variables. So I'm going to erase this. And I'll leave this expression, and I'm going to rearrange this. Every term in here I'm going to think of as a separate algebraic expression. And so I could write this as dt divided by RC is equal to di divided by I. I've just algebraically rearranged that expression, and now I can just integrate both sides. And I'll integrate from 0 to t, and I'll integrate from I naught, I initial, to some final I, I'll call it I. And what do I get when I do this integral? On this side I just get minus t over RC. On this side, what do I get? I get ln of I divided by I naught, right? That will use my properties of logarithms. This is the same as natural log of I minus natural log of I naught. I can write that as natural log of I divided by I naught. And now I'll solve for I. First step is to take e to both sides. And then once I've done that, I need to multiply by I naught. So I naught e to the minus t over RC. That's my current. Okay? And what is I naught anyways? I naught is the initial current when the switch is closed. At that point, the potential across the capacitor is 0, which means all of the drop in potential, that all the gain was across the battery, and all the drop must be across the resistor. There's 0 potential across the capacitor when the switch is first closed. So what is I naught? It is the battery EMF divided by R from Ohm's law. Okay. Right, so when we have exponential functions like this, we have to recognize that it wouldn't make any sense to have some units like e to the minus coulombs, right? I've never heard of anything like that. So that means that the expression that we're exponentiating must be unitless. And this thing down here, which is just the resistance times the capacitor, we often label tau, and that's what we call the time constant. Okay? So resistance in ohms times capacitance in farads has units of seconds. Right? So seconds over seconds cancel, there's no units on that. And this is a natural time scale for things to charge or discharge. It's a not natural time scale for the circuit. Right, now, where would we use this? Where does this factor into actual practical everyday stuff? And one example of this circuit would be to do this. We have a battery, a switch, a resistor, capacitor, all right? And this resistor could potentially be a light bulb. Light bulb is a resistor. So now what we might do is have another wire that goes like this. So the switch can be in open, or it can be either connected to the resistor, or it can be connected to this other wire here. So what do? We close the switch, and it takes some amount of time for the capacitor to charge. And if we wait a long time compared to R times C, then this will be almost fully charged. In other words, well, let's go one step further here. Take a look. The voltage is equal to E minus IR, which means it's E times 1 minus E to the minus T over RC. We got the current, and here's the voltage. So it takes some time for the capacitor to charge up, and once we've done that, it's not going to charge completely. This it approaches a final charge, but never quite reaches it. It approaches an asymptote, and then once we've done that, once we waited a long time, we can then switch the switch. I should draw it this way, actually. This would have been better. Draw the switch this way. Not that it really is that important. Now I can flip my switch into position 2, and we short out the battery. So now what happens? All of the current flows back to try and put the capacitor back into equilibrium. We get an enormous amount of current flowing through that light bulb very quickly, and we get a flash. So this is a flash bulb in a camera, right? Just using a capacitor. And you can see from the graphs on the slide, right? The capacitor voltage asymptotically approaches the battery voltage over time. By the time you're at 5 time constants, it's like 99.9% of the way charged up. And the current drops exponentially as time goes on, as the capacitor begins to charge. Okay. So we talked about discharging already. In this case, the current is just V, the initial voltage across the capacitor, divided by R times E to the minus T over RC, same expression that we got before. The difference is that the voltage across the capacitor is dropping, right? So instead of approaching an asymptote at E when we discharge the capacitor that was already charged to a potential V0, then V versus T also looks like the current, it decreases, right? So it starts from a value of V0 over R, and it decreases asymptotically approaching 0 voltage. Okay, so we can look at the short and long-term behavior for these. For times short or long compared to the time constant, a circuit with a capacitor can be analyzed in simple terms. If we are flipping a switch or something like that on very short time scales compared to the RC, the uncharged capacitor acts like a short circuit. It acts like a wire. And a charged capacitor acts like a battery with an EMF equal to the capacitor voltage. If we're changing things on times that are very long compared with R times C, the capacitor acts like an open circuit. It acts as if there's just an empty spot there where current cannot flow. So that pretty much concludes this lecture. I know it's a lot to take in. If you need extra assistance, there's the Walter Lewin videos, and of course we'll always have our weekly live lessons. So have a good week, and I'll see you next time. Bye.